We've heard so much about the GPU chips AI needs, which have catapulted NVIDIA to the top of the leaderboard. But what about quantum computing? How are they different? And who's making them? Jerry Chow of IBM gave us a tour at the Thomas J. Watson Center in Yorktown, New York.
So this is our IBM Quantum System 2.
Which is the most recent one.
Most recent one. It is also a infrastructure that is built with modularity and scalability in mind, built for data centers, right? So the way to think about it is really this is a modular architecture. What's right behind us right here, this is actually the cryogenic part of it. So inside here, there's actually a cryogenic system which cools down.
That chandelier that we saw in the other room.
Chandelier, yeah. Cools down in the moment there are 3 Heron processors, 156 qubits each, that are cooled inside of this cryogenic infrastructure. And the idea is that over time, that kind of cryogenic infrastructure can be modularly scaled. The footprint can be increased. And then hanging off on the wings over here are actually classical control electronics. So the pieces that generate the signals to manipulate the qubits, read out the qubits, they're all in here, right? And they're actually located right next to it because we need to make sure that they have short time scales for the control and latency. But similarly, as you need to scale to a larger footprint, we can scale the amount of control electronics that are located right around it. But overall, this is really designed with that in mind.
But if I look behind there, it would look like a rack like I see in a data center, like a classical computer.
It would look like classical racks of electronics. We have, at the moment, these are based off of FPGA control board. So this is actually our latest Nighthawk quantum chip, right? And so the Nighthawk is 120 qubits arranged in a square lattice, so it's more connected than we had in the Heron processor in the previous generation. But what you're looking at is the chip mounted into a printed circuit board. This printed circuit board, you can see it has space for where the connectors come down. These connectors come down to bring the signals to manipulate the states of the qubits or to read them out. And then this is basically bolted and mounted at the bottom of our dilution refrigeration systems at 15 millikelvin.
But is this the chip right here?
That's the chip right there.
And other than this is the printed circuit board on the flip side.
Yeah, so it's mounted up into this printed circuit board, and then the signals are being carried out to all these various connectors.
And does one of these chips go into one of those chandeliers?
Yeah, so effectively we're able to fit a varying number of these into cryogenic infrastructure. A big part of that comes down to not necessarily limitation of the size of this, but the size of the kind of wiring that comes down. And so a big push of how we're scaling infrastructure comes down to miniaturizing some of the wiring and the cabling and miniaturizing other components, right, that are within so that we can get more control for larger numbers of chips within the same kind of cryogenic footprint.
So I'm going to go way past what I understand. Back in the old days of sort of electronics, you talk about whether they're rigged up in series or in parallel. Right. If you put multiple chips inside one, is there an analog to
so that
series or parallel?
That's actually a funny point there. Like, so you can place these multiple chips inside. We actually are going to be connecting them with cryogenic quantum links over the next year. So we actually have this technology that we actually demonstrated at first last year as part of a different architecture that we called Flamingo. But it actually allows us to actually scale these and network in a quantum way these various chips together. Wow. So that's one thing. There's already this kind of this strategy for scaling module by module. Another way is actually that there's classical communication networks in the control electronics that also lets you communicate between these chips too, so that you can actually perform a circuit on one, measure the qubits, and in almost real time decide to do something on another chip. So this kind of dynamic circuit piece is also another capability that we have built as part of our overall infrastructure and platform.
Does adding more chips reduce error?
So that piece is, that's not how we're approaching the error correction strategy, right? So the error correction strategy comes down to actually a fundamentally different layout of how we are arranging the various qubits on the device. What that does in terms of having multiple chips really allows us to run a variety of different types of quantum circuits. So you have different kinds of applications and algorithms that might be possible by leveraging this kind of tight coupling of different chips. So this chip is actually what's on. So this is actually a stack of 2 chips. So there's actually a butter side down and another chip that comes on top. That's what you're seeing at the back side of that.
Right.
And this is the piece that gets mounted up onto the bottom of this board.
But there are several of these, right?
Yes, this is several of these.
There's a lot of these.
Yes, these are many Nighthawks, right? So we will cut. We
So
dice
you
these
cut
out
these and then you
and package them
put
and then put them in.
back to front, essentially, on top of each other.
Yeah, and you can see this is 300 millimeter scale.
This is silicon,
So I can
and then it's etched with a sort of lithography
all kinds
process.
of lithography tools and techniques that you would certainly be familiar with for your standard CMOS processes.
For GPUs or
Yeah.
something.
So this is actually the inside of one of our testing fridges. This lab actually we're in is our quantum test and characterization lab. We're
Testing the chips?
testing the chips. So a lot of the either Heron or Nighthawk processors, right? After they come out of fab, we go through a series of qualification steps. Some of them are room temperature tests. Some of them are actually cryogenic tests when they're ready. So that's what this lab is for us to actually qualify and characterize the performance of some of those devices before we decide whether it's good enough to go into, for example, a data center for deployment.
So this basically, you recreate the temperature from what you'll use in the quantum computer.
Right. We effectively recreate the environment in which it would be deployed in, but in order to get out all the salient parts and characteristics of the device to judge that, this is going to be a good one.
And how cold does it have to get?
15 millikelvin, right? So
Okay, so explain that to those who don't think in Kelvin normally.
Yeah, you don't think in Kelvin. I guess 0 Kelvin is absolute zero, right? Minus 273 Celsius, right? And then 0, we're at 15 millikelvin, which is 0.015, right? And if you think about, we always say colder than space because space is in around several Kelvin, right? Cosmic microwave background is in the several Kelvin range. So, orders of magnitude colder than that.
And you get there through liquid helium?
You get that through 2 stages of cooling. Okay, so there's liquid helium itself. If you just had had it as a liquid, is 4 Kelvin. We actually don't use it in its liquid form per se. We have what's called a pulse tube cooler as part of this. It's actually the noise you hear. It's driving a compressed circulation of helium. That part of it gets a large part of the infrastructure down to around 4 Kelvin. It's actually up at the top stage there that gets down to 4 Kelvin. But hanging off that is another closed loop refrigerator. It's called a dilution refrigerator. And it uses a different cryogen. It uses a mixture of helium, which is balloon helium, and helium-3, which is an isotope of helium. So helium typically has two protons, 2 neutrons. You knock off one of those neutrons, you have helium-3. So it's a rare isotope of helium that doesn't exist a lot of places, but we have enough of it in the world. But it is part of the mixture that is used to make these machines actually cool down to that 15 millikelvin